Bismillah. Welcome to ThinkMath. In this lesson, we will study limits of trigonometric functions near zero. Our goals are three. First, to state the fundamental theorems for trigonometric limits. Second, to use their corollaries efficiently. And third, to apply them to evaluate a wide range of trigonometric limits. We begin with two fundamental limits. When the angle x is measured in radians, the limit of sine x over x as x approaches 0 is equal to 1. In the same way, the limit of tan x over x as x approaches 0 is also equal to 1. These two facts are the foundation for almost all trigonometric limits in calculus, provided we work in radians. Let us move to the unit circle to build geometric intuition for the limit of sine x over x. Here is the unit circle centered at the origin, and an angle x measured in radians from the positive x-axis. The point on the circle corresponding to this angle has coordinates cosine x and sine x. The vertical line from the point down to the x-axis has length sine x. This is the height of the point above the axis. The arc from angle 0 to angle x has length exactly x. Because for a unit circle the arc length is radius times angle, and the radius is 1. If we add the chord joining the two radius endpoints and the tangent segment at 1 and 0, we get three lengths: sine x, the arc length x, and tangent length tan x. For small positive x, the vertical side is shortest. The arc is in the middle and the tangent segment is longest. This gives the inequality sine x is less than x is less than tan x. Dividing the inequality by x yields cosine x is less than sine x over x is less than 1. As x approaches 0, cosine x approaches 1, and the constant 1 stays at 1. So the fraction sine x of x is squeezed between two quantities that both approach 1. And its limit must also be 1. This geometric picture explains why limit as x approaches 0 of sine x over x equals 1. Why do we insist on radians in these theorems? Suppose we try to use degrees instead. Let d be the angle in degrees. The radian measure x of the degree measure d are related by x equals pi over 180 times d. If we write sine d over d, and remember that the sine function still expects an angle in radians, this becomes sine of pi over 180 times d, all divided by d. We can factor this as sine of pi over 180 times d divided by pi over 180 times d multiplied by pi over 180 times d divided by d. As d tends to 0, the first factor tends to 1, exactly our sine limit in radians, while the second factor is the constant pi over d. So the overall is pi over 180, not 1. This shows that the clean theorem sine of x over x tends to 1 is true only in radian measure. The limit of the tangent function follows easily the same sine limit. We write tan x over x equals sine x over x multiplied by 1 over cosine x. As x tends to 0, the first factor sine x over x tends to 1 by our theorem. And the second factor, 1 over cosine x, also tends to 1 because cosine 0 equals 1. And cosine is continuous. The product of these limits is 1. So limit as x approaches 0 of tan x over x equals 1. Once we know the basic sine limit, we can derive very useful corollaries. Consider sine of ax over x as x approaches 0. We multiply and divide by a constant a. Sine ax all over x equals a times sine of ax all divided by ax. As x tends to 0, the expression ax also tends to 0. So the fraction sine of ax over ax tends to 1, therefore the limit is a. From this we immediately get limit as x approaches 0 of sine ax divided by bx equals a over b, and the limit as x approaches 0 of sine ax over sine bx equals a over b. And by the same reasoning, the corresponding statements with tangent limit as x approaches 0 of tan ax over tan bx equals a over b. These patterns will appear again and again in our examples. Next, we prove an important corollary involving cosine. Limit as x approaches 0 of 1 minus cosine x divided by x equals 0. We start with the expression 1 minus cosine x divided by x and multiply numerator and denominator by 1 plus cosine x. So 1 minus cosine x over x multiplied by 1 plus cosine x over 1 plus cosine x equals 1 minus cosine squared x divided by x multiplied by 1 plus cosine x. Using the identity 1 minus cosine squared x equals sine squared x, we rewrite this as sine squared x over x multiplied by 1 plus cosine x. Now we split the expression into a product, so sine squared x over x multiplied by 1 plus cosine x equals sine x over x multiplied by sine x over 1 plus cosine x. As x tends to 0, the first factor tends to 1, while the second factor tends to 0. Because the numerator sine x goes to 0 and the denominator tends to 1 plus cosine 0 equals 2. The product is therefore 0, which proves the corollary. Now let's apply these results to several examples. Example 1. Limit as x approaches 0 of sine 2x over 3x. We multiply and divide by 2, so we get sine 2x over 3x equals 2 over 3 multiplied by sine 2x over 2x. As x approaches 0, the fraction sine 2x over 2x tends to 1, so the limit is simply 2 over 3. Example 2. Limit as x approaches 0 of sine 4x over sine 5x. We rewrite the expression so each sine is divided by its own angle. So sine 4x over sine 5x equals sine 4x over 4x multiplied by 5x over sine 5x multiplied by 4 over 5. The two fractions sine 4x over 4x and 5x over sine 5x each tend to 1 as x goes to 0. The remaining constant is 4 over 5, so the limit is 4 over 5. Example 3. Limit as x approaches 0 of tan squared 2x over 3x squared. Notice that 2x all squared equals 4x squared. We rewrite the denominator so that 4x squared appears. So tan squared of 2x over 3x squared equals 4 over 3 multiplied by tan squared of 2x over 4x squared. Here we multiplied and divided by 4, which is 4 over 3 multiplied by tan 2x over x all squared. As x tends to 0, tan 2x over 2x tends to 1 by our tangent limit, so the square also tends to 1. Therefore, the limit equals 4 over 3. Example 4. Limit as x approaches 0 of sine 5x over 2 sine 3x. Again, we want sine over its own angle, so we rewrite sine 5x over 2 sine 3x equals 5 over 6 multiplied by sine 5x over 5x times 3x over sine 3x. Both sine 5x over 5x and 3x over sine 3x tend to 1 since they are based on the same sign limit and it's reciprocal. So the constant factor 5 over 6 remains, so the limit is 5 over 6. Example 5. Limit as x approaches 0 of tan x over sine 2x. We rewrite the fraction as tan x over sine 2x over x. So we know from the corollaries that the numerator tends to 1 and the denominator tends to 2. So the fraction tends to half, therefore the whole expression tends to 1/2. Example 6. Limit as x approaches 0 of 1 minus cosine x over sine x. Here we multiply and divide by x, so we get 1 minus cosine x over sine x equals 1 minus cosine x over x multiplied by x over sine x. We can get the limits for each one of these two fractions directly from our theorem and corollaries. The limit as x approaches 0 of 1 minus cosine x over x tends to 0, and the limit of x over sine x tends to 1, so the whole limit tends to 0. Example 7. Limit as x approaches 0 of 1 minus cosine x over x squared. We multiply both the numerator and denominator by 1 plus cosine x. So the numerator becomes 1 minus cosine squared x, and the denominator becomes x squared multiplied by 1 plus cosine x. So using the identity 1 minus cosine squared x equals sine squared x, the limit becomes limit as x approaches 0 of sine squared x over x squared multiplied by 1 over 1 plus cosine x. We rewrite sine squared x over x squared as sine x over x all squared, and as x tends to 0, this tends to 1. So the first factor tends to 1, and the second factor tends to 1 over 1 plus cosine 0, which is 1 over 2, so the whole limit is equal to 1/2. Example 8. Limit as 2x approaches pi of cosine x over 2x minus pi. We define a new variable, u equals 2x minus pi. Then u tends to 0, and x equals u plus pi over 2. Substituting into the limit, we get cosine x over 2x minus pi equals cosine of u plus pi over 2 all divided by u, which is equal to cosine of pi over 2 plus u over 2 all divided by u. So using the identity that the cosine of an angle plus pi over 2 equals the negative of the sine of that angle. So cosine of pi over 2 plus y equals negative sine y. This becomes negative sine u over 2 all divided by u. We multiply and divide by half. So we get negative 1/2 multiplied by sine u over 2 over u over 2. As u tends to 0, the fraction sine u over 2 over u over 2 tends to 1. So the whole limit equals negative half. Example 9. Limit as x approaches pi of tan x over x minus pi. We want the angle inside the tangent to approach 0. So we let u equals x minus pi. As x tends to pi, u tends to 0. And x equals u plus pi. Substituting gives tan x over pi minus x equals tan of pi plus u over pi minus bracket pi plus u. So it becomes tan of pi plus u over negative u. And using the periodicity identity of that tan pi plus u equals tan u, the fraction becomes negative tan u over u. Since tan u over u tends to 1, as u approaches 0, the limit is negative 1. Example 10. Limit as x approaches infinity of x times sine of 1 over x. When x becomes very large, the angle 1 over x becomes very small. So we use the substitution t equals 1 over x. So as x goes to infinity, t goes to 0, and the expression becomes limit as t approaches 0 of sine t over t. And by our fundamental sign limit, this tends to 1, so the original limit equals 1. Example 11. Limit as x approaches 0 of cosine pi over 2 minus x over x. We use the co-function identity, so cosine of pi over 2 minus x equals sine x. Substituting gives limit as x approaches 0 of sine x over x, which is exactly our basic sign limit, equal to 1. So the limit is also 1. Now it's your turn. I'll leave some exercises for you to solve. Pause the video, answer these exercises, put your answers in the comment section, and I will review them and put the best answers in the next lesson. Each one of these can be solved using the same strategies. Rewrite until you see one of the basic forms, then apply the known limits. Now let us finish with a brief recap. The central results in this lesson are limit as x approaches 0 of sine x over x equals 1, the limit of as x approaches 0 of tan x over x equals 1, plus the corollaries limit as x approaches 0 of 1 minus cosine x over x equals 0. We also saw that these theorems require angles to be in radians. We then used these facts to evaluate wide variety of limits by rewriting each expression until one of the standard patterns appeared. Whenever you encounter a trigonometric limit, look for ways to introduce factors like sine of ax over ax or tan of ax over ax, or to convert expressions with cosine into ones involving sine. With practice, these techniques will become automatic. Thank you for watching this lesson, and I will see you in next videos.